Chapter 3, Examining Relationships. We're going to start with Chapter 3 by discussing scatter plots. A scatter plot shows the relationship between quantitative variables measured on the same individuals. The values of the response variables usually along the horizontal axis or the x-axis, and the explanatory variables usually appear on the vertical axis or the y-axis. Okay? And here's an example. Within this example, we're measuring the speed and the amount of fuel used. As you can see, here's our scatter plot. And to describe scatter plots, we usually look at association and whether it's positive or negative, as shown right here. For more information on drawing scatter plots, look on page 128. What we're going to talk about is correlation. Correlation is the measure of the direction and the strength of the linear relationship between the quantitative variables. Correlation is usually written as R. Here's the formula for finding R. Here's some examples of how R is used to measure the correlation. As you can see in this first example, the points are mostly scattered, so the R will be 0, meaning that they're not really in a linear relationship. As you can see there, we also have some examples as R gets strengthened. But to prove the opposite, as you can see at the bottom here, R is 0.99, and the points are mostly lined up in a straight linear relationship. When R is greater than 0, we say it's a positive association. When R is negative than or below 0, we say it's a negative association. However, R must be between -1 and +1. Okay, now we're going to talk about the facts of correlation. These are also found on page 143 for further reference. The first fact about correlation is that correlation makes no distinction between the explanatory and the response variables. It makes no difference which variable you call x and which one you call y in calculating correlations. 2. Correlation requires that both variables be quantitative so that it makes sense to do the arithmetic indication by the formula for R. We do not calculate a correlation between incomes of a group of people and what city they live in, because the city is a categorical variable. Rule 3. Because R uses the standardized values of the observations, R does not change when we change the units of the measurement of x and y, or both. Measuring height in inches rather than centimeters and weight in pounds rather than kilograms does not change the correlation between height and weight. The correlation R itself has no unit of measure, it's just a number. 4. Positive R indicates a positive association between the variables, and a negative R indicates a negative association. 5. The correlation R is always the number between -1 and 1, as stated earlier. Rule number 6. Correlation measures the strength of only a linear relationship between two variables. Correlation does not describe curved relationships between the variables, no matter how strong they are. 7. Like the mean and standard deviation, the correlation is not resistant. R is strongly affected by a few outlying observations. The correlation in figure 3.7, found on page 137, is R equals 0.634, when all the 51 observations are included, but rises to R equals 0.783 when we omit Alaska and the District of Columbia. Use R with caution when outliers appear in the scatter plot. The next thing in Chapter 3 we're going to discuss is the least squares regression line. A regression line is a straight line that describes how a response variable, y, changes to an explanatory variable, x. The LSRL of y on x is the line that makes the sum of the squares of the vertical distances of the data points from the line as small as possible. And here's an example. We can find the least squares regression line with a few simple formulas. Here is the formula for the least squares regression line. Y hat equals a plus bx. The slope of this line is b equals r standard deviation of y over standard deviation of x. The intercept is a equals y mean minus b x bar. The coefficient of determination equals r squared. R squared equals SST minus SSE over SST, or sum of y minus y bar squared minus sum of y minus y hat squared over sum of y minus y bar squared. If r squared is greater than 0.7, then there's a strong linear correlation. Here's an example. We first calculated x, standard deviation of x, y, mean, standard deviation of y, and the r by using a calculator. And here are our values. Next, we're going to use these values to plug them into the formula. Y hat equals a plus bx, plus you've been giving a peace sign. B equals r, standard deviation of y, over standard deviation of x. So it equals 0.995 times 3.37 over 17.74, which gives us a value of 0.189. Then we're going to find the intercept, which would be y bar minus 0.189 x bar, which equals 5.31 minus 0.189 times 22.31, which gives us a value of 1.09. Then we just plug these into the equation to get y hat equals 0.189x plus 1.0. For more information on the least squares regression line and the least squares regression charts, look on pages 149 to 167. The next thing we're going to talk about is residuals. Residuals is the difference between the observed value of the response variable and the value predicted by the regression line, as shown here. Residual equals observed y minus predicted y, or y equals y minus y hat. The mean of the least squares residuals is always 0. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line, meaning that if you take these points out, it will change the regression line, as stated earlier in our facts about correlation. For more information about residuals, look for pages 167 to the end of the chapter around 1